Hello everyone, welcome to my precision RCA workshop again. So in this workshop, we'll do like some mathematical modeling to tell how to do RCA quickly and why the brainstorm RCA cannot solve a problem quickly. So agenda here is we're talking about what challenges for RCA because for the past histories, we spent a lot of time on RCA, but they didn't address the root cause and failure will come back again. So we are second one is the modeling of the brainstorm or why RCA brainstorm RCA cannot working. And then third one we're talking about how to make a breakthrough. Then we have a case study here to see how we do quickly RCA, and then we got a summary. So the challenge here is really like everybody, all engineers, technicians, and managers, even some of the directors have some experience that in any companies we do have factors. These factors always come back. Some actually could be chronic there for long times, and eating away a lot of maintenance cost, even cause a lot of production loss as well. So if we cannot solve the problem, so whatever team will do will be low our expectations and normalize it, right? So for the goal of this presentation, we try to find out why RCA cannot do correctly by mathematics modeling here. And we are introduce some the method we use engineering method to address the root cause as quickly as possible, and then to solve problem as quickly as possible, right? And then also will be helpful engineer and manager to open eye how effectively like RCA can be done, right? But some of the RCA, from my experience, RCA could be took about 2 months, like 10 people to study case. But then the result could be like still same problem again over there, right? So here we just give like one of the mathematical modeling here. Uh, in this case, we only use like 10 possible root cause. But in real life, it could be 20 or 30 possible root cause. Then the probability for you to find the genuine root cause even low, even less, right? Some of the RCA have done before. The companies spend more than 30 years, but the problem is still there. So now let's looking at the mathematics ways. So this principle will be applied to all the RCA, right? Correct. So here, after RCA studies, potentially you can find the 10 possible root cause. We are coming from the different team member over there, right? And then scenario one here is if we put a little report, go to the manager to get approved. What is the possibilities we found root cause? Scenario here, one is, okay, if only one root cause, this root cause contribution to 90% of failures, right? Then the probability of we find the root cause is like 10%, correct? Yeah. Scenario two here is if only two of the root cause is genuine root cause, and one root cause contribution 60% or 35%. So the percentage here is 1/10 times 1/9. So opportunity for us to find root cause is only about 1%, right? So scenario three here is if we do have three genuine root cause, yeah, then the probability is like 1/10 times 1/9 times 1/8. So this is about like 1.4 thousandths of possible. So this is scenario why in some case the company face some chronic problems and they will keep on doing RCA, but still cannot find the root cause. Because usually it takes you about 2-3 weeks to find the root cause, and then take another like month to working on the root cause, right? So this is the period that you need to working on that, and in 1 year it may be working on 2 or 3 times, and then if keep continue on, potentially you can be continue on 50 years, 100 years, but the problem is still there. So how can we make a breakthrough, right? This is a headache for everybody. This is really like it's pain for technicians, like operations, even for our maintenance managers, plus our production managers, right? How can we make through, right? Because we know the problem is there now. So if we can quantify the root cause, then it's very easy for our team to working on the root cause, and also we can assign the minimal resource we need to solve problem, correct? So here we just give example. If we find a number 269 contribute to 40%, 30%, and 25% of the failures, right? Then the solution will be guaranteed to find the solve problem, right? So and the probability will be converted 1.4% solvents to 100%. Yeah, in theory it is, right? Perfect. But how can we do that? How we do that, right? So how we do that? We're looking at one case here. This case is a real case I was worked before, right? So this case is we do have one deep well pump. The team over there working on this problem for 6 months and working on the motor overloading. But every time they try to start the pump, try to pump the liquid from the vessel, but every time they get overloadings, right? And then what we do there is we have a meeting together with them and we found the problem. And what we do there is looking at the system over there. We spend half an hour to find root cause, and then half an hour later, after the preparations, everything was set up over there correctly, the pump will start perfect, smoothly. And let's looking at how we do that, how do that quickly, right? If we look at here, we give us a simple drawing here. So this one is a motor, and here is a pump, and we're pumping this one to outside, right? So that in this case here, what we use here is a pump performance curve, and one of the equation here is the power of the motor equal to Q times H. Q means flow rate, H means the head, and the times the lambda here is density, and divide by efficiency here, right? So at that time, we are asked the team over there how they are started the pump. Every time they told us that every time they open the discharge valve at the same position. That means according to this performance curve, it always working at 100% here, right? Or the working position here. So no problem. That means power and need is no difference as before, correct? But then we ask then at head here is the same, but then we ask then, well, what any difference to the densities, right? So the team tells us before the fluid there is condensed, so the density is 0.6. Now because of the operation upset there, a lot of water coming to the vessel, the right side. So we know that the water density is 1. So now let's do the calculation, compare with the new motor power need, right? So it's so P1 divided by P equal to lambda E divided by lambda. So it's 1 divided by 0.6. Now the new power needed is 1.6 times. So it means power needed increased 66%, right? Now we find the root cause quickly because of the density change causes the motor power, right? And then what we do there is we ask the team over there to close to 100% close the discharge valve, and then after the start of the pump, gradually open the discharge valves. Because here, what we can change here is we can reduce dramatically all the flow here, and in that way, the power needed for the pump at the startup to the minimum, right? So after they are prepared, half an hour later, they start the pump. gets through and gradually pump the water out, then the condensate come in, then the motor running smoothly over there, right? So let's do some summary here. Just like Sun Tzu, the most famous military uh, expert in China, said about the art of war. Said, no, if you want to you need to win the war, you need to know the enemy, you need to know yourself, and then in 100 battles, you will never lose, right? You will win 100 wars. So what I hear we're talking about RCA is the number one rule here is like your team should have enough knowledge about the equipment and the process. Yeah. Number two, we also need a very strong technical leadership here. In the previous case study here, like before we are the team over there always like working this way, right? First, we ask electrical guys to check, right? Electrical guy check everything, and then we ask the millwright to check everything, and then we ask the instrumentations. Then I will process. So everybody check the systems, but they cannot find their system is wrong, right? Only when you're looking at the whole system over there and looking at how the motor power, how the power needs, how to calculate, then you can find the root cause so quickly. Because in these studies, we only need one is data from the operators, the densities, right? So it can solve your problem so quickly. Number three is for RCA, we always need to focus on what a change. So this change can be from design, can be from manufacture, can be from operation or maintenance, right? If you can really find the changes without boundary or design or rated design ODS, you can find the root cause quickly. And number four here, like this is my theory, right? Usually for any of RCAs, in most cases, the root cause usually is one or two, right? Maximum three. If after RCA study, we found, okay, you got like a 10, 20, 30 possible root cause, that only means we didn't understand the system correctly, and we not studied deep enough over there to find out the root cause yet. Maybe we need to go back over there. And also the other I will share with you is we have to believe ourselves. You know, most of the cases, the operation people don't have confidence for themselves, and they always will rely on the manufacturer, design company to figure out the root cause for them. But here, I challenge you for the team here is they do have a confliction of interest here. Even if the manufacturer know what the root cause, why they are needed to tell us what the root cause? Because if we tell them what the root cause, we are not come back to them to buy their spare parts, to buy their service, right? But sometimes, some case, it can be cost them like $1 million or loss from the manufacturers. So here, just as I said, RCA can be do quickly and precision ways here. Hopefully everybody can learn from this study. And if you have any questions, so if you have any like a need or any like help you want from me, please contact me. My information, my phone and email is on this page here. Even you can visit my website and see what kind of service we provide to you. A good day. Thank you, everybody.